Thank you, sir. Oh,
Can we start?
just a minute, sir. Very good afternoon to all you. Hope you are doing well and following the social distancing. I am Professor Sanket Unde. Welcome you all for 5 days faculty development program on research opportunity in robotics and automation, organized by Bharati Vidyapeeth deemed to be University Mechanic Department, Pune. For this session, we have with us dynamic, motivated personal, Mr. Pravin Bell, sir. He has completed diploma in electronics and robotics, radio engineering, and degree in industrial electronics. He has more than 25 years of experience. He is founder, member, director, and chief technology officer at Indiasoft Technology Private Limited, Pune. It is founded in 1993. Indiasoft Technology Private Limited has been providing set up at art engineering simulation software and laboratory simulation to corporate educational engineering and R&D organization across India from last 25 years. Exposure over last 25 years to leading the technologies in various fields of engineering, including mechanical, electronics, electrical, mechatronics, automation, robotics, and so on. Work in various simulation software, including products and domains such as MATLAB, Simulink, uh, SCADA, CNC, power electronics, electrical power systems, thermodynamics, PLC, automation. He is speaker for faculty development program for more than 300 institutes. Without taking much more time, I welcome you, sir, and request you to take the charge of this session and enlightening the participant with your words. Please take charge, sir.
Okay. Thank you. Thank you very much. Uh, we'll begin directly. Now,
Yes, sir.
my name is Pravin Bell. I'm the director and CTO of Indiasoft Technologies. I'm also ex-alumni Bharati Vidyapeeth College of Engineering. I passed out in 93. Okay. Now, I personally handle this product automation studio. And since the heading of today's session is research opportunities in robotics and automation, so I don't want to get into too many basics except for a basic demonstration. But we'll be touching upon a lot of technologies because I think the intention of this entire development program is to what is the type of work students are doing, MTech students are doing, certain other faculties, how are they using this software for research, etc. So we'll not be getting into anything basic like, I'm making a small assumption that everybody is sort of familiar with hydraulics, pneumatics, and PLC automation. At least some basics everybody is aware of. And we'll take it from that platform onwards. So in short, I want to cover these few things in today's session. One is people who do not know about Automation Studio. So very brief introduction, maybe 10 minutes on how Automation Studio is used. What is the interface? What are the libraries? How we can do that? Then in automation, since hydraulics, pneumatics, PLCs, electrical is a big part. Proportional hydraulics and catalogs. These are very, very widely used in industry. And this is where a lot of work happens in a lot of students are doing research, a lot of PhD people are doing research in this particular area because this is a more advanced area of automation studio. Then also we'll be touching upon OPC, DA and UA technology because OPC, DA and UA has today taken a very big importance because of the IIoT and Industry 4. And OPC has now become the backbone for Industry 4 layers and the gateway to the clouds. So we will be touching about that technology. We also will be touching on SFC, which is the alternative programming language for PLCs. We'll be seeing certain student projects and certain research areas. And in the end, for 5 minutes, I'll just brief upon the mechatronics and robotics solutions which my own company has to offer and the work we have done. Also in tomorrow's session, there is one of my friends, Mr. Anil Ambore, he's going to be conducting a session from Eaton Technologies, and they are also a user of Automation Studio. So he has a session tomorrow. So he'll be concentrating more on what Eaton does in aerospace, if I'm if I'm correct. And he may not be covering all these modules tomorrow. So I'll be doing that today. So Automation Studio comes from a company called Farmic Technologies from Canada, and it is a bundle of all these modules. It is a multidisciplinary software. So we have hydraulics and proportional hydraulics. So normal hydraulics, what we teach in colleges is, the standard circuits, meter in, meter out, reciprocating, etc. These are very basic circuits, but the 60 to 70% of the industry work happens in proportional hydraulics. And proportional hydraulics is where you're using proportional valves, servo controlled valves, and these are used in earth moving equipment, deep sea exploration, let it be hydraulic cranes, lifts, automation, different types of areas, power steering of vehicles, etc., where analog type of control is required. So you have things like joystick, steering wheels, etc. We also have pneumatics and proportional pneumatics. Then coming to the actual power of Automation Studio, we have a module by the name of fluid power component sizing. Sorry. So fluid power component sizing is where the actual design or the calculation work happens. So if someone wants to build a particular circuit of a, let's say, a piston pushing a load of 2 tons at an angle of 45 degrees, and with a system pressure of 70 bar, and extraction has to happen exactly in 7.5 seconds. So how do you do such type of calculations? This is where this module comes into handy, and you don't have to go back to Anthony Esposito or Mujumdar and look up the equations to try and solve these problems. Then a very important module, powerful module, is the mechanisms and mechanical linkages. Now, this is where the real life loading conditions are calculated by the software. For example, let's say a piston is moving a cantilever arm, which is mounted on a pivot, and this cantilever arm is carrying a load, and it is moving along, it is getting pushed by the cylinder, which is also on a pivot, and the angle of inclination changes. So forces of gravity are acting on it. A lot of things are happening. How will such loading actions happen? So this mechanisms and mechanical linkages handle such type of loading conditions. Then we have troubleshooting and diagnostics. Then if you come to the red area, this is where the entire control section of Automation Studio is. So if you see, we have electrical controls, JIC and IC. So anyone wanting to do work like electro-hydraulic, electro-pneumatic circuits, batching of cylinders, 5, 6, 10, 15 pistons, all working in a particular sequence, you can use an electrical circuit. European and American standards, we have both of these. Then we also have 4 types of PLC ladder logics: Allen Bradley, Siemens, IEC, and LSIS. And in the, I think around January, Automation Studio version 7 is coming, and they're going to be including the Mitsubishi PLC ladder logic also. So you can create ladder diagrams and interface them directly to hydraulic pneumatic circuits, and you can simulate them. Then we also have something known as SFC, Structured Text ST, and GraphSet. Now, this is the alternative language to PLC programming. And in the industry, if you see the market share of PLC programming, I would say around 60 to 70% of work is happening in SFC and ST rather than the standard ladder programs. And in fact, a lot of MSME tool rooms, CITD, Hyderabad, etc., have started introducing SFC into their courseware, and this because this is required in the industry. Then we also have digital electronics, in which we have things like AND gates, OR gates, SR, JK, D flip-flops, verification of De Morgan's theorem, etc. So we can use these components. Now, another very powerful module in the software now is a mathematical block diagram module. And this is something like Simulink. So any people wanting to do research in a particular area by using certain mathematical models interface to hydraulic pneumatic circuits, they can directly now use it within Automation Studio itself. Even though Automation Studio has things like MATLAB Simulink APIs for direct software in loop simulation, we ourselves have a mathematical block diagram, and I'll show you how this comes into handy when we are trying to do research level work in this particular area. Then we also have HMI control panels, where you can build all types of control panels, dials, gauges, analog, digital meters. We can import 3D components into Automation Studio parts. You can assemble them and you can make them operate by using hydraulic pneumatic circuits. Then if you see the black section, this is manufacturers, catalogs, and catalog manager. Now, this is the most important module in the industry because this contains more than 50,000 components from more than 45 to 50 manufacturers all across the world. And this has components such as Eaton, Danfoss, Hydraforce, Parker. All these companies have catalogs in the professional version of the software. It is not therefore educational. And the catalogs by the model number and all the internal characteristics fed into that component are available in Automation Studio. You can directly drag, drop, and start building your industry circuits. Then if you see the green section, we have interface box for 24-volt interface to hardware kits. But what is more important is we have OPC client and server support just now. So OPC is open platform connectivity. And if you see MATLAB, Simulink, LabVIEW, PLCs, DCS, SCADA systems, they all today support OPC as a communication platform. And this is the future of communication because including your IoT gateways, etc., all are using OPC as the backbone. As far as the corporate users, these are the entire list of corporate users: Komatsu, Eaton, ABB, John Deere, Caterpillar. They are all using Automation Studio to do various type of work. I don't want to get into too many details of these. So we'll close down this particular slide and we'll come to the working copy of Automation Studio. So I don't want to build too many circuits online, but this is what Automation Studio looks like. There are hundreds of colleges in India who have now already implemented Automation Studio, and they're users and they're doing the college practicals, projects, etc. So before we build any particular circuit, certain background properties I want to show you of Automation Studio. For example, we now have an accuracy of almost 0.1 milliseconds of a simulation pace. So you can do circuits which are that accurate. Okay. We can do things like thermal simulation, cavitation simulation. For example, certain settings like acceleration of gravity, because when loads are getting lifted, a piston is at 0 degrees and is moving at from 0 to 90 degrees vertical position. The load handling capacities change drastically, and this actually handles all such conditions. Also in the background, if you go to the fluid section, we have a fluid and line manager. Now here, if you see, there is an entire list of fluids available here. And each of these fluids have their viscosity properties. How do they behave at what temperature? And usually in undergraduate level, people do not bother about these, but anyone trying to do research level work, you can access all these properties and they're used during simulation. Okay. Then initially, air was considered as the only gas for pneumatics. But right now, things like butane, carbon dioxide, helium, hydrogen, oxygen, propane, they have all been included as gases for using doing pneumatic circuit simulation. And the software also understands the compressibility factors of these gases and what is the volume content in the lines which are connecting these components. We also have materials, different types of materials: iron, steel, copper, brass, cement, internal roughness of these pipes. Then even the line types, DN, these are the industry line types, polished steel, etc. These are all there in the background. So anyone wanting to do work at that level, they can access these properties. So we'll just build one small circuit online, and there is a lot more to show. There are too many things to show. In fact, I hope I get to show as much as possible in these 2 hours which we have. So I'll be building only one basic piston extraction circuit. Okay, and I'll lay out these components. I join these components. So in a matter of seconds, I build a simple piston extraction circuit. Okay. Now, before we simulate the circuit, if you go to the piston and you check the piston properties, we have things like, is there a external mass on the piston rod? Is it at an inclination? What are the stroke lengths, diameters, etc.? These are there. We also have things like, you can customize this entire cylinder. Do you want to put damping springs? What are the spring stiffness ratios? Is there a brake on the cylinder? Do you have a carriage? what type of position sensor you want to put, force sensors, speed sensors. You can customize this entire cylinder from scratch. Even in the walls, we have total control over the internal flow curves of these walls. Now, this specifically comes into use when people are trying to do research. For example, Jadavpur University, they were using certain walls from Eton, in which they wanted to go and modify these internal flow curves of all these walls here to make it match to the industry component. So they were able to do that because of Automation Studio. Uh, Also, if you want to change a particular spool, there are different types of spools available in Automation Studio, hundreds of spool types. Also, things like if I want to build a 7x3 valve, I get only 7x3 spools available here. So this is totally customizable, full power over the internals of the software. Now I will simulate this particular circuit and I operate my lever. You can see simulation happening. While simulation is going on, I can change the pump displacement, cracking pressure of my pressure relief valve. You can see it is moving fast now. Okay. Now, this is okay. The circuit is behaving, it is moving. But what is more relevant is that I need to take measurements, etc. And for that particular purpose, I have different types of measuring instruments. I have these dynamic measuring instruments where I can point at a particular component. It automatically detects what can I measure for that particular component. This is automatically detected. I say, okay. If I say I want to measure across 2 points, it automatically says differential pressure. I simulate the circuit and I get my readings on my measuring instruments. Okay. Now these are happening very fast. So I need to take plots, which I can analyze later. Okay. And for that reason, Automation Studio now has different types of plotters. So at any given moment of time, I can open up to 4 plotters. So 2 plotters as a function of time plotters, a third plotter y as a function of x plotter, and a fourth plotter, which is a 3D plotter, y as a function of zx plotter. So the first 2 plotters are for time-based plotting. For example, I can drag a component, put it on screen. It is going to show me the plots against the x-axis as time. So I simulate this particular circuit and I can get my piston extraction here. I can plot these values here. These plotters are fully customizable. I can take measurements on them in this particular fashion, okay? Because I need to accurately see my piston extraction times, etc. So at one time, I have 2 y as a function of t plotters. If I want to plot 2 variables against each other, let's say pressure versus flow or something, I can use this plotter. And 3 variables against each other, I can use a 3D plotter. So I have very powerful plotting options available here. I can export these plots. I can say copy plot image and directly put it in Microsoft Word, PowerPoint for my dissertation or for my project report. That is possible. Okay, so this is a basic hydraulic circuit. Also, while simulation, things like I have cross-section animations for these components. Okay, these are there. These are useful in teaching, no doubt. So I have these cross-section animations. Yeah. So this is a basic hydraulic circuit. Now going forward, there are more than 5,000 components in Automation Studio. So it's a very, very huge library. Now, let's say a small example of an air distribution system. Now, this is not there in Anthony Esposito, but this is found in Mujumdar Pneumatics. And air distribution systems, usually a lot of teachers over the years have called me up, how do I do an air distribution system experiment for my students? And there are solutions in Automation Studio. Now, for example, if you go to the Mujumdar textbook or even on Google, there are certain definitions for air distribution system, certain limits have been given. That for example, the main line pressure drop should be maintained less than 0.03 bar. Okay. And let's say the pressure drop between the first point and the end point where the actual pneumatic instrument is working should not cross 0.1 bar. So basically what we do is we first take the main line, 150 meters and 15 mm diameter. And if we simulate this, you can see that the pressure drop is 0.258 bar, which is very high and it is not a feasible pneumatic system. So let's say I change this to 25 bar. I say okay. And now if I simulate my circuit, you can see it's 0.025 bar. So this is an acceptable pressure drop for a main line of a pneumatic distribution system. Now this is a very small part, but the main problem comes when you're trying to design the rest of the pneumatic system. Because in the industry, there are different type of air distribution systems. Okay, these are the different types. There's the inline conventional network, there's an octopus type, and there's a closed loop type. So the closed loop type is supposed to be the most efficient because extra air which is there anywhere in the loop, it gets diverted to the point where the maximum air requirement is there. So if you take a larger system like this and we simulate this, okay, you can do this in much detail. For example, if you see this 0.097 bar is the pressure drop between the starting point here and the end pneumatic instrument here. So that is what our specification defined. Also, at this particular point, you can see air is coming from both directions. That is because the air requirement here is higher. And because it is in a closed loop fashion, you can see the extra flow coming here. So in this way, you can play around with the diameters, the lengths, the pressure drops across maybe the TL sections of the fittings, etc. And you can go ahead and develop an entire air distribution system. So simulation software like this can be used. Now, this itself becomes a area of, sort of a research project, or you could take up a practical student project of maybe a air distribution system which is there in a car service center of maybe Volkswagen or anything else. You can pick up projects like that and you can design these in-house. Now coming to a very powerful part of the software is something by the name of sizing module. And sizing module is where the main designing happens. So anyone, see what happens is in educational I've seen that design, the word is very conveniently used, because if you connect 2-3 components together and it is operating in a particular fashion, it is considered a design. But design actually means that it has to be designed in a fashion to do a particular amount of work under particular conditions. So let's say we take a simple example here that this piston should extract from 0 to 100% in maybe exactly 2.5 seconds. So how do I achieve a condition like that? Okay, so I first go to my pump, and my pump I go and I note down the rated flow. Rated flow here says 120 liters per minute, because this is the flow which is coming from the source, the pump, and this is going to operate my piston. So I note down this value 120 liters per minute. Then I go to my cylinder and open the sizing sheet module here. This is what the sizing sheet module looks like. On the left hand side, you can see there's an entire list of components here. And each of these components has got a list of equations. There are hundreds of such type of equations. Okay. Now, what these equations mean is that if you see at the bottom here, there's an input side, okay, and there's an output side. So on the input side, you enter the values which are known to you. These are the known variables, and the software will automatically calculate the unknown variables. Okay. And if you see here, the equations used for solving these sheets are listed here for reference, and the calculations are done here. So now I need a particular equation in which, what do I know? I know that I want a piston extraction time of 2.5 seconds. I enter that value. Piston diameter is known as 50, and piston side flow, I say 120 liters per minute. The moment I enter these values, the software automatically calculates the stroke of my particular piston here. This has been automatically calculated. I say pass this value to my cylinder. I say okay. I close this sheet. I open a plotter. And now I'll simulate my circuit. Okay. I'll stop the simulation. And if I measure the piston extraction time here, you can see this is 2.5 seconds. Okay. So in this way, I can do a lot of these calculations here. I have to choose the equation of my choice in which I know the known variables. Software is going to use the empirical equations in the background and do the output calculations. So there are a lot of these components available here which can directly help me to do design based problems here. So this module is very, very heavily used in industry for these types of calculations. So that was the sizing module. So it can be used in a lot of research also. Another very powerful module is that how do we attach forces and opposing forces and loading conditions in Automation Studio? Because undergraduate diploma levels, we are just looking at circuits which are operating, but we are not actually calculating what is happening when loads are applied, how does it behave, what happens, etc. So for such a case, we will take one small example of this is a simple circuit which is mounted on the front of a bulldozer, and this bulldozer is pushing sand. Okay. So as the bulldozer moves, the opposing force of the sand increases over time. Here, the sand piles up, and as the piston extracts, this is going to increase the opposing force. Okay. So now how do I tell the software that such a condition is being applied? So I go to this double acting cylinder, I go to force curves, I go to resistive force curve, and here you can see, I can see 0 to 100% on the x-axis. So on the x-axis, this is the piston extraction, 0 to 100%, and this curve is the opposing force here. Right now it is pound force. You can choose your units, DA, Newton, Newton, etc. And this is the opposing force which is going to act on my particular cylinder. Okay. And as an engineer, I want to go and plot the linear position of my piston and the piston side pressure which is built up inside my cylinder here. Okay. So now I'll simulate this particular circuit. And I want to show you certain interesting observations. I've paused the circuit, and you can see that the piston has stopped at around 75 to 80%, because at that point the opposing pressure was so high, the opposing force, that it could not push more than this. At the same time, you can see there's a spike in the system. You can see it in the graph here. So now you as an engineer, how do you go around improving this circuit? You can go and change the diameter of the cylinder. You can change the system pressure of the pressure relief valve. You can put an accumulator in the circuit. There are various options you can try out. So in this case, let's say I'll go and change the cracking pressure of my pressure relief valve, and I continue the simulation, and you can see the piston now reaches the end position here. So such type of work can be done in Automation Studio. You can do all these trials and build upon these circuits, because in the industry, this is how they actually use this particular circuit design software. So that was resistive force curve. Now, obviously, we have an entire list of electrical components in Automation Studio: push buttons, solenoids, contactors, relays, coils, etc. And you can build electro-hydraulic, electro-pneumatic circuits. And I have seen that a lot of people, when they're doing student projects or maybe even research work, there are two types of work they do. One is at a very basic component level and a lot of mathematical calculations. And the other is the system design. For example, maybe 25 or 30 pistons working together, doing some batching operation, how to coordinate, how did the entire control system worked out for this particular case. So that is the controls and the actual part. Whereas some people do hardcore work in the hydraulics, piston diameters, tensions of springs, pressure relief valves, how does that hydraulic portion work. So it depends on what nature of work you want to do and simulate. You can pick up projects in this particular area. So in this case, we've taken a HMI panel here. We've taken an electrical circuit here where there are two solenoids which are connected to this valve here. And there are two sensors on this cylinder here at 0 and 100%. If I simulate this particular circuit, we can see we get a self-reciprocating action here. So since this circuit is, this software is a fluid power software, if I increase the displacement of my pump, it moves faster now. The circuit responds accordingly. So this is an electro-hydraulic circuit. Okay. Now going ahead, we are coming into the area of proportional hydraulics and pneumatics. So let me open up that particular area. So now proportional hydraulics and pneumatics is where we use proportional devices. For example, steering wheel, joysticks, set point input devices, PID feedback controls, etc. And the applications for these are very huge. Almost in every field of hydraulics, pneumatics, we require proportional control. Okay, so even if you see the cabin of a Caterpillar machine, it has all these proportional devices which are there in the cabin itself. Okay, these are used. Okay, and the components which are there in the industry are very different. So for proportional control, we have things like foot pedal, joysticks, manifold type of valves. We have PID controllers, feedback loops, etc. So basically in the industry there are three types of valves. One is the basic valve, which is an on-off type of valve, very low cost, which we see on all trainer kits in all colleges. They're typically used. Then we have the proportional valves and the servo valves. Now this is very rarely seen in colleges, except for I don't know, in my experience, not more than 4 to 5 colleges I've seen proportional valves or servo valves trainer kits in the colleges. So in proportional valves, we have solenoids on both sides which accept analog signal. So here on the valve diagram, if you see, there's an arrow which indicates that you can give an analog signal here. Whereas if you see a servo valve has a servo motor mounted on the valve, and that is what controls the internal spool of the particular valve. Now, for academic interest, if you see on the left hand side, this is a proportional valve. And if you see, there's a diagram here which shows the spool and the tank and the pump ports here, PA, TPB, these are the ports here. And if you notice this particular area where my mouse is moving, the spool and the body, there's an overlap here. You can see this here. So if this overlapping area is more than 3%, it comes in the proportional valve category. Whereas if you see a servo valve, if you see there's hardly any overlap here, it is 1% or less here. And that is why these valves are much more expensive and much more accurate also. So if you see this, the dead band zone, this is where the overlap happens. This is a dead band that as the spool is shifting, what is the output flow? So if this is 3% or more, it will be proportional valve category. Less than 3%, it comes into the servo valve category. And so if you see, this is a proportional valve, how it operates. We have solenoid coils on both sides. Okay, so this is a proportional valve. Whereas if you see a servo valve, it is different because there's a servo motor mounted on the particular valve. These are very highly accurate valves. And there are a lot of these manufacturers of servo valves in India also, Eaton being one of them. Eaton has a very powerful valve by the name of Eaton Access Pro valve. I'll be showing you a circuit of that also. Okay. Now, having said that, okay, we have, this is what proportional hydraulics is supposed to be. Yes, sir? Can I continue?
Yes.
Okay. So now, having said that, we also see we'll be skipping between, shifting between a lot of applications because everything is interconnected. So now Automation Studio in the professional version has this entire list of catalogs available here. Okay. Now these are available in the professional version, educational also, but under annual maintenance contract. And if you see here, we have things like Parker, SMC, Parker, Eaton, Hydac, Kasapa. There's an entire list of, see, Danfoss, Poklane, all these are there. These are catalogs. There are more than 40 to 50,000, more than 50,000 in fact. Industry catalog is there in Automation Studio, and if these can be downloaded, and if you want to see them in the software, I will show you. If you come to home, there's this catalog manager here. Okay, this menu is not available usually in the educational versions. And here, if you see, there are these entire catalogs available here. For example, Danfoss proportional valve group. Now, PVG is a concept which is very widely used in almost all type of hydraulic equipment. In fact, I had a few students who did work in Danfoss PVG valve category, and one of them even published a paper, which was a research paper for a hydraulic forklift machine. I'll be showing you that particular circuit. So what is a PVG concept? Okay. So PVG is a brand name of Danfoss proportional valve group. There's an equivalent with Eaton also. Eaton calls it stack valves. Stack valves. Danfoss calls it proportional valve group. Now, if you see here in this image here, where all these levers are there, when you're building a circuit for a hydraulic, let's say tractor, or it could be earth moving equipment, it could be excavator machine. What happens is you cannot have 20 valves mounted on an iron bracket and pipes running all over the place, etc. Okay, so we need something much more compact. Okay, so what happens is, if you see this levers here, 1 2 3 4 5 6 levers, each of these levers is operating a particular valve which is within this particular casing here. So this is a group of valves which has 6 valves cascaded into each other. So depending on your application, for example, if you see this particular green machine here, this particular machine requires three actuators to be operated, and that is why if you see this group of valves at the bottom, 1 2 3, you require 3 valves here. Okay, so what you take 3 groups of PVG valves, you stack them together, you screw them out, the internal ports automatically connect to each other, and you connect to it the cylinders and the pump section, etc., the external components you connect. And this concept is very, very widely used. Let it be John Deere, Caterpillar, any tractor manufacturer, earth moving equipment, they all use these manifold blocks. And these are rarely seen in educational sector because they do not know of particular.
Sorry to interrupt you, sir. Hello, sir. Your audio is break. Hello, sir. Hello, sir. You're not audible, sir. Hello, Pravin, sir.
Can you hear me?
Yes, sir.
Can you hear me now?
Yes, sir. Continue,
Yes,
please.
yes, sir. You are audible.
I think someone muted me by mistake. I didn't do it. Okay, I'll continue. Okay, so now in this PVG concept, there are different varieties of PVG by Danfoss. So let's say we come to the PVG 120 module here. So if you see, there are these by catalog number, part number 155G50, this one. If I pull out a component, this is a pump side module. Okay, I pull this here, I put it here. Then there are different accessories for pump side. Now these are the internal regulating devices. This plugs directly into this particular module here. Then there are these basic modules here. I pull out a manifold block. I get it here. It plugs directly into this pump side module here. There you go. Then depending on what type of operation I have, I can directly put out a proportional valve here. I'll just zoom into this. This proportional valve, I can directly come and plug into this system here. So that is the beauty of industry catalogs, because these are ready-made components directly available from the manufacturer. Not only that, but the internal flow curves. If you see this is the behavior of the valve, how it behaves internally when it is operated, and the internal flow curves of the spool. When the spools are opening up, what is the flow curves? So even these are fed into the particular software. So only at MTech and research level, people bother about these, because below that, people are really not interested at UG level. And since our FDP is about research interests of automation and robotics, so this is how we go ahead by building an entire PVG block. Okay. Now, before we simulate this, I want to take you through what is proportional control, and then we'll come back to PVG. Like I told you, we have to keep jumping between applications because they're all in some way interrelated to each other. Okay. So now, in proportional control, we have been teaching students PID, proportional integral derivative controls. And students, let me tell you, more than 80 to 90% do not understand what is the application of a PID controller and how it is to be used in industry, and what is the use of this entire PID controller. So what we do is we typically tell students that, okay, I have a PID controller, there's a set point value which comes in, and it is going to operate something, and we take a feedback through a sensor. This comes back to the PID controller, then there's some error calculation which happens, and it goes and controls the process. But they've never been able to see this practically happening. And trainer kits for PID controls, not too many colleges have them. Typically, even if they have them, they'll be for temperature level or some other type of applications. And then what we do is we build this circuit, and we typically use MATLAB, Simulink, LabVIEW, or any multiphysics software. We build a mathematical block diagram, and we show them that, okay, if you change the PID values, these are the graph behaviors. Okay. And there are very, very strong research papers which people have done by using mathematical block diagrams to do hydraulic pneumatic control, and how these PID circuit diagrams are used to control such type of applications. In PID tuning, there are different methods. So if you see the manual tuning method, there is, you set the integral derivative values to 0, increase the proportional value to such a value that you get ultimate oscillations. Then you cut down the proportional value and do certain things, and then you get a stable response, etc. Similarly, we have Ziegler-Nichols method also, which is typically taught in MTech level courseware. So these are used. And this is what we typically do in MATLAB and Simulink. We build this block diagram, what you see on the right, and we conduct this experiment. So now, how do we achieve the same thing in Automation Studio? So in Automation Studio, we have a PID controller. Wait, I'll open up another circuit, not this one. Okay. Now, actually, this circuit has got 3 circuits. I'll explain. In fact, there's a research paper on PID control for hydraulic pneumatic circuits. So we'll take this first circuit on the top here. Now, on this circuit on the top, we have a cylinder here. On this cylinder, we have, if I go to the builder, there is a position sensor mounted on this particular cylinder. So the feedback coming from the cylinder, which is 10 to minus 10. This is the left and right position, end position of this particular cylinder. Okay, so that is the signal coming from the position sensor. If you see the proportional valve, this proportional valve, we have to scale the solenoid signal also, -10 to 10. Because in the automation industry, let it be any type of a control system you're trying to build, signal scaling is very important. You cannot apply a 0 to 5 signal to an actuator which is set at -10 to 10. Behavior is going to be very totally erratic here. So you have to make sure all these settings are done here. Okay, so the cylinder is sending up position signal to the control device. This is the PID controller. Okay, then as a set point input device, what we are doing is we are giving a step wave like this. This is more of a combination of a triangular come square wave, and certain things, because see, I'm treating you as let's say MTech research level of simulation. There are certain things which have to be considered here. That the cylinder, this piston is moving from 0 to 100%. Okay, at both the ends of the piston movement, there is the cylinder wall. So the piston goes and hits the cylinder wall. So if this piston hits the cylinder wall, this piston is going to get damped by the cylinder wall. It will go and get stuck there. Okay, and that is the reason, if you want this piston to oscillate, we cannot let it touch the end position. So if you see, this graph is not set to -10 to 10. We have left gaps here. So at the bottom it is -9, at the top it is 8 here. Okay, so what this means is when the piston should not reach the end position and hit the cylinder valve and get damped, we want to see oscillations when this piston achieves this position but not get damped by the cylinder valve. That is the reason we go and set this graph from -9 to 8. Okay, then these two signals come to the PID controller. PID controller will do the error calculation. If you see here, we have set it in PID activation error mode here. Okay, and that is going to send the signal to the proportional valve. So we simulate this particular circuit here, and what we do is, first we'll go and set the proportional value to 8, integral 0, derivative 0. And if you see the graph now, this is how it is behaving. So the blue line is the input signal from the graph, and the yellow line is the piston movement here. So you can see we've got a condition of oscillations here. Next, what we do is we go to the proportional value here, and we set this value to, let's say, around 3.5. We set the integral value to 1. Derivative will keep it at 0. And if you see this, we have attained very fair PID tuning, you could call it here. Okay. Now this is what typically even a block diagram in MATLAB and Simulink can do. Okay. But now what is the difference? What is the power of a hydraulic simulation software like this? So I'll prove that to you. Let's say I go and change the proportional gain back to 8. Let's say I change the integral gain to 0 and derivative gain back to 0. I've got my oscillations again. But now I go to my pump and I change my pump displacement and I reduce it. I reduce my pump displacement. You can see half the oscillations have disappeared here. So the total behavior has now changed. And this is now what you cannot account for in a software like MATLAB, Simulink, LabVIEW, etc. Because there you're not taking into consideration the internal flow curves of the valves, the viscosity of the fluids, temperature effects. Is there a damping spring put in a particular circuit? A lot of these external factors which affect the tuning of a PID circuit in hydraulics, pneumatics control systems are not taken into consideration in a mathematical model. Or then you have to make sure your mathematical model is so detailed, done in so much detail that you've taken into consideration all these properties here. Okay, so now this was using a ready-made PID controller which was there from the Automation Studio library. And during the start of the demo, I also told you that Automation Studio now has a block diagram module also. So I'll just vertically tile this. Yeah, there you go. Now the circuit at the top here was using a ready-made PID controller, which was this CTRL99. The second diagram here at the bottom is using a block diagram, which is this block diagram. Okay. Now this is a mathematical block diagram. So in Automation Studio, what you can do is, if you want this control system to be more complex, instead of just a PID, you want to use some feedback, feed forward, something in combination, or maybe you want to add another signal which is coming to this adder device here, or you want to make some changes in this control schema here, you can use the block diagram model of Automation Studio. So we have, let me open this. We have a block diagram module here. You can see this blocks here. You have input, continuous, filter, discrete. In continuous, you have second order transfer function, first order transfer function, different type of mathematics, adder, trigonometry, logarithmic, power. So all these block diagram modules, just the way Simulink has them, you can directly build these control systems here and link them directly to hydraulic pneumatic circuits in the software. So the Automation Studio hydraulics part will take care of all the dynamics of a hydraulic circuit. The mathematics will take part of the control side, and they will both interact with each other and behave perfectly. So this could be an area for MTech and you could say research area. A lot of work can be done in this particular section here. And at this point, I would also like to show you certain things. For example, where is that PPT gone? Okay. At this point, I want to show you this particular list of student projects and research areas. Now, for example, there was this Miss Gauri Salunke, VIT Pune, and in a third year, she did a particular project on a hydraulic forklift. Okay. Now, this hydraulic, I'll be showing you circuits of this later on. Right now, I'll just give a brief description. Now, this hydraulic forklift used different things. One was on the left-hand side for the steering section, there was a Eaton steering valve manifold block used. On the right-hand side, there was a Danfoss PVG32, which I was telling you about for the lifting and the tilting section. So this was there. This paper was published. It was accepted also because there are a lot of design conditions which are there in this particular system design. For example, steering wheel should have full rotation in exactly 3 seconds for the entire this thing. Then there are dynamic loading conditions on the pistons because the tilt cylinder is supposed to handle 4 tons of load irrespective of which cylinder hits the load before the other. So piston synchronization problem. And for that, a flow divider was used. Then the main lifting ram, that was the static load after the tilt cylinders were actuated, and that had to lift the load from 0 to so much height and particular timing. So there are a lot of design conditions in this particular circuit. So this was one project. Then there was another hydrostatic transmission system. This is Dr. BLDA Halkatti Bijapur project, which was done by someone there. And this was a electrically controlled variable displacement pump, and obviously a PID feedback loop used in this for a symmetrical and asymmetrical cylinder. And there was a particular definition for this particular paper, and the simulation was done in Automation Studio. So this was the screen captures from this particular research paper, hydrostatic transmission. Okay. Then Jadavpur University, they've been doing a lot of research and this thing in hydraulics and control systems area. So Dr. Saikant Mukherjee, if you see this image here, this is a linear motion electro-hydraulic system. So a lot of feedback, controllers, hydraulic, proportional valves, etc. They all use in combination, and they do a lot of defense projects also. So this was almost 4 years back when I visited them, and I had taken these photographs. One of the presentations there. For example, this one particular research project here is from Jadavpur University, was this balancing table here. So there are multiple pistons mounted on this particular balancing table, and the Eaton Access Pro valve was used. Why I was shifting between catalog components and professional hydraulics is that Eaton has this particular catalog component known as the Eaton Access Pro valve, which has a PID controller built onto the valve itself. And they were using this valve in their projects for this particular control system here. Okay. Then the MTech batch of students also did another student project of a walking robo here. Now this also used the Eaton Access Pro valve for feedback, and there were cylinders in this particular walking legs of this robo here. And these cylinders, the cylinders available in the market were not small enough to fit into that particular bracket. So they came to Eaton Kharadi, Pune, and they sat with the R&D team here, and they actually got this particular cylinders manufactured here with a feedback position sensor. So this is one of their projects which they had done. Then there was another project, Government College of Engineering, Amravati. This is a student project in which there was a cotton baling machine and PLC automation of a cotton baling machine. This was one project. Then MIT College Pune, few years back, a bunch of students, they went and created a test bed circuit for a Eaton hitching valve. A hitching action is there behind a tractor here. So when a log of wood or something has to be held up, it has to be hitched and it has to be held like that. And for that, this particular entire one block which you see is a Eaton hitching valve block here manufactured by Eaton. So they use this block, they went to the company, they built the entire test bed around it, and they created a project out of it. Then, okay, College of Engineering Pune, MTech Mechatronics. Now they have two projects which were IIoT based, and one of them was a paper which was published. And the first system, this was around 3 years ago, was a PLC based fluid power system, IoT system. So what the student batch did was they built a real pneumatic system here. What you see this pneumatic on the plywood table is a clip manufacturing machine. So you put a piece of metal, these cylinders go and press that particular clip, they make a clip out of it. And every time a clip is manufactured, there's this IO box here, IO card. This monitors the strokes of the pistons. This is capturing that. Then the capturing of this piston strokes were taken into Automation Studio PLC. And then Automation Studio has a OPC communication, and that data was taken from OPC and sent to the cloud. So if you see a ThingSpeak, is the cloud platform which they used. So they wrote a little programming in Python, and they sent this entire data to ThingSpeak from Automation Studio. And on the ThingSpeak server, the number of cycles were captured here. Okay. And on the reverse side, they built an Android application in which this data was represented here. So on the Android application, they had a start and stop button, and it used to count the number of cycles here. So this was one project by COEP Pune, MTech Mechatronics. A second batch of students, which is just very recent, around 6 months back, did a IoT-based system for elevator applications. So COEP Pune has a elevator simulator, which you see on the right-hand side here. This elevator must be almost around 7 to 8 feet in height. It is that big. Okay. And the student actually traced the entire elevator PLC logic. So the circuit which you see at the bottom is the PLC logic for that particular elevator. Then instead of incorporating and changing any electricals on this PLC, what the student did was he pulled out parallel connections from this elevator circuit and not disturb the original working of the elevator. And those signals were sensed. And he had aim to the experiment that I want to capture the number of door opening, door closing. He had this aim for what data you need to capture from a IoT based system. Okay. So this paper was published. So this also used ThingSpeak, Automation Studio interface using the OPC gateway. And this was a MTech student project, and Dr. Sudhir Patil, he and this batch of students, they published this paper also. It is available on Google. So you can go and find this paper also. So this was one project. Then there are certain dissertations, MTech Mechatronics. Uh, this was a system which was an entire system for color and material sorting conveyor system was built by the students using a PLC module, and they built it in Arduino as well as Automation Studio PLC interface. So they did two versions of the same project. So this is also one project. Okay. Then if you see abroad, people are doing work like these are all research papers. If you go on Google, you can do Automation Studio research papers, and you can find a lot of areas, what type of work these people are doing. So this is a hydraulic steering system using Automation Studio software. This is Vietnam Maritime University. Then in Romania, uh, since Automation Studio has a mechanism manager and 3D assembly also, a project for a cylindrical robo was created by using Automation Studio. I'll show you 3D and mechanism manager also in Automation Studio. But these are the areas in which people have done projects and research work. Then this was the SFC and the HMI dashboard for the same project of the cylindrical robo. Then another hydraulic application here. Then in Malaysia, there was another hydropneumatic driveline paper. In China, there are a lot of them. They've been using it very strongly. For example, fractional order PID controller function block in Automation Studio, automatic welding filled tube hydraulic system based on Automation Studio, hydraulic system of air tightness measurement, tubeless wheel based on Automation Studio. A lot of these are all research and projects. Then SRM University, India, Ghaziabad, smart electrical control system using PLC and HMI using Automation Studio. This was another work. Now, excuse me. So another, just to give an example, now let's say one particular area of interest. See, we are looking at opportunities for research and robotics, like in automation. So what type of research can you do? For example, now this is a circuit of a hydraulic winch. A winch is a hydraulic motor operating a cable which is going to lift loads, etc. So one particular circuit was made like this. I'll open up that circuit and show you. So there's a hydraulic section here in which there are valves, cylinders, motors, pumps, etc. But the dynamics of this hydraulic winch, this winch here, were defined in the block diagram of Automation Studio. And here, if you see, the winch specifications can be changed. The base radius, winch width, the mass, 5,000 kgs, damping ratio. These are defined in the mathematical block diagram, and that is acting as a load onto the hydraulic system here. So this is a research area where you can simulate the dynamics of this winch in a block diagram module or a mathematical module, and then interface it with the actual hydraulic circuit here. So this is another area. This nature of work can happen. Also, for example, let's say hydrostatic transmission using block diagram module. Hydrostatic transmission blocks are manufactured by all companies like Eaton, Hydroforce, Danfoss, etc. So these are the hydrostatic transmissions, but the dynamics of the particular wheels, etc., those are defined in the mathematical model. So torque on the front right wheel, vehicle mass, rear wheel radius, resistance coefficient, etc. So this is defined in the mathematical model, and that is directly applied to the hydrostatic transmission in the hydraulic circuit. So such type of work can be done. These are the research area we can look at, For example, this is the Eaton Access Pro proportional valve which I was telling you about. This is what Jadavpur University was using. So if you see, this is a valve here, and on the valve itself there's a PCB and there is a PID inputs here. So externally you can directly control the PID values into the valve itself. Okay, and this can do the proportional control of the valve here. Okay, so now let's look at okay. A strong module which Automation Studio has, which can be used for MTech and other research areas, is the Mechanism Manager. Okay. Now, Mechanism Manager is where you can actually define real life loading conditions. For example, these are dynamic loading conditions. Here you can see there's a piston, there's a valve, and there's a joystick which operates this particular proportional valve. But this particular piston is actually mounted on a mechanism like this. So the entire cylinder is on a pivot at the base. Then the piston rod is also connected to a pivot. It is connected to a cantilever arm, which is also on a center pivot. And on the end of the pivot arm, there's a load of minus 100 Newton acting from top. So how will such a circuit behave? So that can be done by using this mechanism manager. Okay, so Automation Studio has this. There's a module to specially build these mechanisms here. So if I simulate this, you can see in the first instant itself, because of the load acting in the minus y direction, it is already pulled out the piston, and this cantilever arm is already buckled like this. So now I can use this proportional valve to go and lift this particular load like this. So these are the types of mechanisms you can create in Automation Studio. So this is a very simple mechanism. I'll show you something more interesting. Am I clear? Is everybody following this?
Yes, sir.
Okay. So now let's say another application like this. Now Automation Studio is very strongly used in ISM Dhanbad. ISM Dhanbad is become IIT ISM Dhanbad now a few years back, and they have a lot of mining equipment there, mining projects. And I was there a few years ago, and surprisingly, and I was very shocked of different types of PhDs happening there. Maybe the entire premise itself. At one given moment of time, there were 720 people who had pursuing PhD in ISM Dhanbad. I was a little shocked. And in the hydraulics pneumatics section itself, there were like 7-8 of them trying to do different types of works in hydraulics pneumatics. Now, one of the projects was rock breaking mechanism, in which different cylinders were mounted on a particular bracket, and the piston rods were welded together with an iron plate. Okay, and this was going and breaking the rock. So it was more of a ram type of a mechanism. And the requirement was that how do I create this mechanism in a hydraulic circuit? So this is not exactly a ramming mechanism, but this demonstrates what type of a mechanism can I create in Automation Studio. So if you see in this circuit, on the left-hand side, there's one cylinder here, which is connected to a valve and a pump. And the right-hand side cylinder is just connected to a reservoir. Okay, this is a standalone cylinder. But in real life, we've taken a metal rod and we've clamped the two cylinder rods together. Okay, and that has been defined in this particular mechanism here. This has been done here. So now we'll simulate this and see the behavior. So if I simulate this particular circuit and I operate the piston on the left hand side, it is going to pull out the piston on the right hand side. So this is how they behave. Okay, so this is a real life condition. Now if I go to the second cylinder here and I go to something known as troubleshooting, and I say jam the particular piston here, I say jam the second piston, and now if I try to simulate the circuit and operate the left hand side cylinder, it cannot pull out the cylinder on my right hand side. I'll simulate this again. You can see there's a jerk in the mechanism. I'll count to 3. On the count of 3, just watch this particular. Let me zoom into this. Just watch this particular horizontal bar here. 1, 2, 3. You saw that? So this simulates such type of real life mechanisms. It could be multiple linkages, it could be an entire pivot chain, etc. Carrying different loads, center of masses, etc. etc. A lot of things can be done in this particular mechanism manager. Now, Automation Studio also has 3D. Now we have our own 3D modeler, but it is not as powerful as CATIA, Ideas, SolidWorks, etc. But we can do Boolean-based 3D modeling. Or you can import parts from other 3D software into Automation Studio, assemble them, create the joints, and then link them to hydraulic pneumatic circuits. So initially, I'll show you a small circuit here, and then I'll show you a larger excavator circuit in which everything is used together. So if you see this, these are two components from external 3D software. A joint has been created here, and that joint has been linked to this cylinder motion here. So if I simulate this particular circuit here, you can see the piston is operating the mechanism here, 3D mechanism. So such type of things are possible. Now, if you see a larger circuit here, I'll show you a larger circuit now. Okay. Now, if you see all these things on screen right now, see what have we covered? Number one, if you see these blocks here, these are proportional valve groups. 1, 2. You see this? This is what Danfoss PVG 32 valve group was. 1, 2, 3. So there is a valve group here. 1, 2, 3, 4 valves are used here. So we have used catalog components here. Second thing, at the top here, we've used proportional control. So there's a joystick and there's a PID controller here. So in one excavator machine, we've used industry components, we used PID controllers here. Then if you see this mechanism here, this is the mechanism of the excavator arm here. So this is the body, the purple and the green is the body, and these are the pistons mounted on them, which are going to be operating the particular circuit, real life conditions. Okay, and all this is linked to the 3D diagram in the background. So multiple things which I showed you in the last half an hour are now all going to be working together here. So this is a bucket. Okay. This is the second joystick. There's also this steering wheel here. Okay, so if you see this itself has become a large size area in which there are so many things you can do. You can use an industry component, build a proportional valve group, use PID controllers, use hydraulic motors, use pistons, create the mechanism for it, see how the loading conditions are behaving, and then see the entire response. So a lot of things, though this is still not the full circuit of a excavator. Excavator circuits are much more complex than this. This is just the actuation section here. Okay. So this was one circuit. Another circuit I want to show you is that of a steering mechanism. Okay, so now this is a steering mechanism, and if you see the hydraulic section here on the right hand side, you see this entire block here, ACC76A6, the entire dotted line. This is one hydraulic steering block. So we have a servo valve here at the center here. Okay, and then there is this round component here. This is known as a metering device. So for the PID controller, this metering device gives the feedback. So depending on the flow on both sides, there's an angular movement, and this is used as feedback for the power steering. And then that is operating the valve, the pistons, which are going to be controlling the tires here. Then obviously this is the actual mechanism for the entire system. This is what the mechanism looks like. We'll simulate the circuit. We simulate this. We operate the steering wheel. So again, in this particular circuit, we have a combination of industry catalogs, proportional PID control behavior, mechanism manager for real loading conditions, and the 3D model. So there's a lot of scope depending on what you want to do, because if you see in industry, if students want to pick up projects, you want to do particular research in a particular area, you want to do it in the control section, or you want to pick up an industry component like a steering block, a manifold block, hydrostatic steering, there are braking devices, there are lots of components available in the market. Those themselves can be used as a base for a particular project or a research area. Now, for example, Eaton has a particular steering valve. Okay. Now, Farming Technologies Canada.
Sorry to interrupt you, sir. You are not audible. Hello, sir. You are not audible. Hello, sir. You are not audible. Also, screen is not visible.
Okay, now?
No, sir.
Can you hear me now?
Here, yes.
I think someone is muting me. When you're muting all, I'm getting muted by someone. Okay, can you see my screen now?
No, sir.
Okay, I'll stop sharing and I'll start sharing again. 1 minute. I'll share it again. Now?
Yes, it
Can
is
you see my
visible, sir.
screen?
Yes,
Okay.
sir. Continue, sir.
Yeah. So this was a defense application in which what happens is automatically a sensor is triggered, and at the end of the runway there is a net which is on the floor level, 0 degrees, and that net has to be activated. It comes up and it captures the entire aircraft which bangs into this particular net. Okay, and this was a real project by Fluid Power Group in a DRDO. And certain small this is not the complete circuit. It was not opened out to us because it's under non-disclosure. But certain main sections of this circuit, I can tell you. There are two pump assemblies here, double pump circuits. If these pumps fail, in parallel, there's a hand pump. So even if the electricity fails and these pumps do not operate, we have a backup of hand pumps here. Okay, so these pumps are operating. Then there are 3 accumulators used here. Now these 3 accumulators hold enough of charge that even if electricity goes off, 3 aircraft, one after the other, can be captured by the fluid supply given through these accumulators. Okay. Again, this system is on 24/7. So these accumulators are charged by using these pressure switches here. So to maintain a particular pressure, these pressure switches switch on and off. So it's sort of automated hydraulic system. Okay, and then we have the actual pistons here, and these pistons are going to be lifting the net. And here you can see this is the typical meter in, meter out configuration. So there are settings on that particular hydraulic system that this net should come from 0 to top in a particular amount of milliseconds. So that certain design conditions. The other design condition was also this, that between these 2 pistons, these cantilever arms which are attached to the pistons, there's a net, and this net has a self load of 900 kgs. Okay, so when the pistons are at 0 degrees, the net has 0 weight. But as the net is lifted up, the loading of the net itself is a sort of a curved loading pattern. Okay, so that loading pattern is there. That has to come into the design system. Then after these nets come up, after that the aircraft has to ram into the particular net and capture the entire load. So there were a lot of small design considerations which are there in this entire system. So if you see that this entire thing becomes a sort of a research cum project area. And to simulate the net action, this mechanism manager was used here. So these are the 2 pistons here on which the net was actually connected here. So we'll simulate this particular circuit. We'll switch on the first motor. We'll switch on the second motor. You can see the accumulators are charging here. Pressure switches are working here. Okay. Now after this is done, I'm going to raise the net now. Okay. So I'm going to raise the net. The net has been raised. I'm going to pause the simulation. So if you see here, this particular graph, this curve which you see here where my mouse is, this is the load of the net from 0 to 90 degrees. That is from 0 to, as the net is rising up from 0 kgs to 900 kgs. So the software even captures conditions like that here. So that is very comfortably handled. So simulation is continuing here. Now to ram the aircraft into the particular net, we have created a graph signal here, which has got a heavy spike in that. So I'm going to trigger the graph. And you can watch the mechanism when the aircraft rams into the net. So if you see, it buckled slightly, but again it went back. That means it was able to capture that 60-ton force into the speed at what it was coming. So it was able to handle the entire load of the aircraft. So such type of design systems, and there here in the graph also, if you see, this is where the aircraft rammed into the particular net here. So such type of analysis, design, research, projects can be done in Automation Studio. There's a lot of scope here. So this was one real life project. Then coming to certain student projects, I want to show you those also. Okay, one was the paper which was published by this girl who was doing internship with me, VIT College Pune. I'll show you her circuit. Okay. Now this was now see, this girl had come for internship in the holidays of second year. She was little intelligent, I must say. But before the semester of hydraulics pneumatics started, she came here. She learned a lot of hydraulics. She learned the software and built this entire circuit on her own. And since we were so impressed, we created a paper out of it, and it got accepted. So what is this circuit all about? This is a hydraulic forklift in which a lot of things have been taken into consideration, design point of view. Number one here, there is a flow divider. And this flow divider is a component available from a lot of manufacturers which divides flow as per a particular ratio. And it maintains steady flow irrespective of the loading conditions. Okay, so it maintains synchronization of flow irrespective of the opposing loading conditions. That is a function of a flow divider. And this flow divider had to divert 30% of the fluid on the left hand side and 70% of the fluid on the right hand side for the lifting mechanism. So on the left hand side, there is a Eaton steering block here. Okay, if you see this, she did not take this directly from the catalog. This was component by component assembled in Automation Studio here. So there's an entire study on the steering block of Eaton here. So this steering block was used with a servo motor, metering device here. These are the pressure relief valves here, and the steering cylinder, double rod cylinder. And there was a design consideration that for the rotation of the steering wheel here, this was going through a PID controller. There was a design condition of loading and the accuracy of this power steering also here. So this was a power steering section here. Okay, and this was the power steering response here of the PID controller. This was the left hand side. On the right hand side, this particular section, if you see here, is a Danfoss PVG32 valve group, which I was talking about. So this is a PVG32. So there was a separate study on this because this is a load regulating, flow regulating type of a valve group. So this was modeled. 70% of the fluid came here. Then there was a tilt cylinder here. Now tilt cylinder again requires piston synchronization. So another flow divider was used here. So that for erratic loading conditions, I hope these are here. Yeah, see. So these are the erratic load conditions of 4,000 kgs. So one cylinder, we are subjecting it to an opposing force like this. The second one is again a different type of a curve. So whichever load hits any of the cylinders before the other, synchronization should not get lost between these two cylinders. That was the condition. So we simulate this particular circuit, and even though those opposing forces were erratic, these two cylinders were still perfectly in tune with each other. And then the lifting mechanism, which was a static load, to operate in I think 4 or 7 seconds or something, 4,000 kgs. So this entire circuit was designed by this particular student, and this became a paper. So this was one circuit. Then there was another one, aircraft I showed you. Okay, Amravati College of Engineering. Now, why this particular circuit is important is because this is a cotton baling machine. Now, this was a machine manufactured by some manufacturer, and it was manual in nature. Manually, they were operating it. So, number one job was first to automate it. So, this PLC was designed by the students. Okay, so that was the control section. Another thing was that these three pistons operating here, the piston rods were welded together with a plate. That's what made this project more interesting. And that was done by using the mechanism manager. So you see that there are three pistons, and there is one metal plate which is fused to the entire three piston rods here. Also, these three pistons went up to 50% for 3 strokes, like it is pressing the cotton, and the last stroke it goes all the way. So there were different types of design conditions involved in this particular circuit here. That's what made it interesting. I think after this it will go full stroke. Yeah. So this is more of an automation type of a project in which various conditions were required here. That was one. There are more to show, but I think we are now 5:35. So I'll just briefly show this one circuit, and I want to take you into the area of OPC and that type of technology. Now, especially for MTech and research areas, people who want to use block diagram combined with hydraulics pneumatics, this is a circuit here, okay, in which this is a hydraulic winch. So we have the hydraulic section here, and this is the winch. And the winch loading conditions, dynamics were modeled in the block diagram module of Automation Studio. So this is the entire block diagram with the formulas here on the right hand side. Okay. So this itself could be a project or a research paper if you pick up some nice case study and want to do something in this particular area. So this is a block diagram interacting with a hydraulic pneumatic circuit. Automation Studio also has MATLAB Simulink co-simulation if you buy the API module, but you don't need that because we ourselves have a block diagram module within the software itself. So this was hydraulic pneumatics, PLCs, mechanism managers, etc. I want to take you into another area now, and that is which is very important for what do you say, automation and IIoT communication between hardware, software, etc. And that is OPC, because OPC is now the backbone for a lot of data communication. So this was one of the lectures I had given in COAP, I think around 1.5, 2 years ago. So I've just retuned the PPTs here. OPC is a standard of data exchange. It is platform independent today. Okay. And I'll just show you the important areas. Okay. Now in OPC, OPC stands for Open Platform Communication, and there are two versions of OPC. One is OPC UA, which is on the right hand side, and on the left hand side, what you call as the classic OPC, which is known as DA, DCOM, that type of OPC. So what is the difference between the two? The classic old type of OPC required a OPC server here, which was Windows based, and all the clients were also Windows based. So what you actually needed was, if you want to communicate, let's say, LabVIEW signals directly to Automation Studio and control a particular valve, okay, then you required a Windows based network with a OPC server residing on the network somewhere. So everything was passing through a Windows operating system. Then what happened was, because this platform got so famous, a lot of companies started adapting to this way of communication, and it led to a point where they wanted to get rid of Windows as the base for this communication. And that is why OPC UA, Unified Architecture, was invented. This is not new, this is quite old, UA also. And OPC UA means that you do not require a Windows network. Today, if you buy a PLC in the market, let's say Siemens S7 1500 series, or I think NX1 from Omron, there are the certain range of PLCs which have OPC embedded into the PLCs themselves. So you see here, this is a PLC here. This looks like this is Advantech PLC, and this is a Adam Advantech IO communication module. Both of them have OPC embedded into them. All you need to do is put a TCP/IP cable between these two and give the IP address of each other, and they start exchanging signals with each other. Okay, there's a software for doing configuration. So today in the market, if you buy a DCS SCADA system, or let's say you buy a processor card, or let's say there's MATLAB, there's Simulink, all of them support OPC today, and you can communicate between them. I'll show you an example of this also. In the industry, uh, let's say this diagram here, it shows Siemens PLCs, Phoenix, Beckhoff, Schneider, Allen Bradley, Mitsubishi. All of them can talk to a OPC server. And from the OPC server, you can also connect to databases. You can plot graphs, trends, etc. All that can be done through the OPC server. In fact, if you see the CERN project, now CERN is the Large Hadron Collider, which is in Geneva today, the world's biggest experiment. And the cooling system and the monitoring of this cooling system is based on the OPC platform here. So if you see here, there's 25 kilometers of tunnels under the earth, and in which the protons are circulated at a very high speed, almost close to the speed of light, and they exploded in a particular chamber. And there is entire nitrogen cooling in this entire system here. And so there are around 14 stations and 200 data points which are monitoring the temperature in this entire 24-kilometer length. And the top is a company, TOP. OPC server is monitoring this entire cooling system here. So OPC in CERN, we'll not get into too many details, but there are 180,000 OPC items, 1 lakh front-end devices here, and around 10 lakh parameters supervised by the DCS system in the so this is a OPC based monitoring system here. Okay, so even those people are using OPC as the backbone. Now coming to IoT, IIoT, and Industry 4. How does OPC play a role here? Initially, IoT was there. It started with smart devices, Internet of Things. So we had things like smart plugs, baby monitors, cookers, watches. You could start a air conditioner at home from a watch remotely, etc. So this is where IoT started here. Then it migrated to IIoT. That is, how can I use this for industry? And we came up with Industry Internet of Things. And in Industry Internet of Things, you have your manufacturing floor where there are a lot of sensor data put there. You have to capture a lot of data and then send it to the cloud. Now, and Industry 4 stands for the analysis of all this data which is captured and use it for things like preventive maintenance or auto-tune, some sort of batching, etc., etc. Now, I have seen this confusion in a lot of colleges, professors, that anything they want, they say, I want Industry 4, I want IIoT. But the definition and the problem statement of IIoT is very important. What are you going to do with IIoT? The definition and the conclusion is very important. For example, if you have a CNC manufacturing shop floor, and on that CNC control panel, which could be Fanuc, Siemens, Simoneric, whatever, you're capturing data, let's say of the amount of hours this particular machine is operating. That data is captured, let's say time of rotation. I mean, how many hours that machine is operated. That data is captured, sent to the cloud. And then you say, okay, after so many hours, I need to do preventive maintenance. And before that machine breaks down, I will need to go and do the preventive maintenance. And I get an alert. Now, this is an actual application of IoT. You can't just say, okay, I want an IoT and something connects to the cloud. I'm seeing some plot somewhere and that becomes IoT. No, that is not the intention. Your problem statement has to be very clear. Okay. So if you see on a manufacturing floor, I have this factory level. There are PLCs, SCADA, HMI, all this is on the factory level here. And the entire backbone is an OPC gateway which goes to the cloud. This data is captured in the cloud, and then this data is represented, pushed onto maybe iPads or mobile phones, etc., and sent to different people. Certain decisions can be taken. That data can be analyzed. It can, certain type of simulation can be done on that data, and certain steps can be taken. So the IoT, the entire loop is important as to what are you planning to do. Now, for example, Varroc engineers, they have shifted to Industry 4 with IoT and OPC. That is one company, and Datonis was the company which gave the cloud solution. Altizon brought Datonis. So a lot of data from the manufacturing floor was given to the cloud, and from there all the decisions were taken, batching, how much products have been produced, what is the cycle times, and what is the preventive maintenance, etc. A lot of decisions were taken after that data was captured. Okay, so now, for example, like I told you in IoT, what you want to do is very important. What data points do we collect in Industry 4 to make it a successful IoT experiment? There is sensor data, there is barcode data, there's number of jobs processed, number of jobs rejected, number of jobs assembled, number of assemblies depending on sizes, pneumatic pressure is detected, temperatures are detected, height of certain units can be measured, variations in assemblies, processing time of stations, robo cycle times, number of jobs available in storage. So if these are captured and some valid experiment is created out of this, then we call it a real IoT implementation. So yes, Indiasoft also, we have these modular production systems in which we have created an entire IoT platform with real experiments here. So this is required. So why I've explained this was the importance of OPC. So now let's see OPC working. Okay, I've got some circuits for OPC. So for OPC, we first require a OPC server. Okay, so I'm using OPC DA, the old version of OPC. This is what an OPC server looks like. This is a simulation server. So on this OPC server, I create these tags. If you see this, I've created the data tags, analog, 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 boolean, boolean. These are the data tags I have used in the background. Now these are going to be used as data exchange. So this is going to behave as a data exchange server. Okay. So now what do I do is, let's say I take a third party HMI software, Winlog. Okay, where is it? Okay, Winlog. This is a freeware, shareware available on the net. And in this, I've created a dashboard. Okay, I've created the dashboard here, in which there are 2 dials, gauges, and 1 slider signal here. Okay, these have been connected internally to this OPC server here, to this analog tags here. Okay, then in Automation Studio, now I have a hydraulic circuit, which is an aircraft landing gear. Let it open. Okay. We have 10 minutes left, so I'll try to wrap up before that. Okay, so this is a circuit in which there's a HMI panel here of the cockpit of an aircraft. There's a 3D landing gear here, and this is the hydraulic section of the landing gear. In Automation Studio, if you see in the communication manager, there is OPC DA and there's OPC UA. Both are available here. So Matricon OPC simulation server, which I had triggered in the background, is appearing here. You can see this. Okay. Then there is groups and there are links. So these signals from Automation Studio are going to Matricon OPC server here. And WinLog on the other side is reading those signals into a different software altogether. So from Automation Studio, I'm going to be sending these signals via the OPC server to another software here. So I simulate this particular circuit. Okay, once a particular pressure is attained, one light will come on. Okay, it has come on. Now I'll open the carriage. Wheels have come out. And look at the right hand side also. If you see this section also, this is a different software altogether. I'll retract the carriage. You can see on WinLog, the dials and gauges, the signals are passing through here like this. Okay. So this is the way two different software of two totally different technologies. One is the HMI SCADA software, one is Automation Studio. They are talking to each other through OPC. So that is how data exchange happens through a OPC server. So this happens with hardware PLCs also. That is also possible. So this is how OPC works. And today, because of the IoT relevance which has come in, a lot of gateways have come into manufacturing. A lot of people are manufacturing gateways to IoT. Now, what is a gateway? Now, gateway, for example, if you're looking at software point of view, let's say on my machine, I have something known as a Cogent Data Hub. Now, this is one example of a software which has an IoT gateway. Okay, this is Cogent Data Hub. If you see in Cogent Data Hub, there is OPC UA, there is OPC DA. In OPC DA, you can see it has already recognized the Matricon OPC server here. Okay, so this is there. And in Automation Studio, I'll open up a circuit which is connected to this gateway. Now, this gateway, if you see, has options of things like MQTT client, MQTT broker. Okay. Now, MQTT client, MQTT brokers are the protocols which talk to services like Amazon Web Services or your Microsoft Azure, etc. These are the clients which actually talk to the cloud platform and send data from your local machine to the cloud for IoT, data capture. So OPC DA will take data from Automation Studio. MQTT client sends it to the cloud. So that is what these gateways do. So a lot of gateways now available in the market. So this could again be a very strong area for MTech and research areas. How can you implement these gateways? There are hardware gateways also available in the market. Okay, those are also available. And in this, I want to do something like I want to plot trends of certain signals coming from Automation Studio. So this is Automation Studio. It's a simple circuit. There are two sensors which are getting triggered. So these two signals are going to the gateway. If you are right now, I'm not connected to Amazon or Azure, but Amazon or Azure, the cloud services will have typical dashboards like this. Okay. And the gateways will send data to these dashboards here. So you have to set a channel. You have to set the parameter values. You have to do all the settings for the variables, and that data is read into these dashboards. So this circuit I'll simulate. Okay. And in Cogent Data Hub, you can see this data is getting captured here. So the same data can be now sent to the cloud via the MQTT or the REST protocols which are available. So this could be another area for a lot of MTech and research areas. You could create these gateways. You can experiment with Amazon Web Services, Azure, etc. Not only this, even software like, let's say, Kepware. Kepware is another Kepware. Okay. Okay, this is Kepware. Kepware is a software which has multiple drivers for different another 100 200 types of PLCs, etc. Kepware also has OPC support. You see this? These are the signals from Automation Studio, and this has an entire section for IoT gateway. So these can also, Kepware can also send data to the cloud, to Amazon Web Services or Azure or any of the IoT cloud services. So this is again another area where a lot of work can happen. This is not too many people experimenting with this. College of Engineering Pune, COEP, they've done 2 projects already. I showed you in the beginning. One was the elevator and the pneumatic clip making machine. So they have been doing work in this particular area. So this is another area a lot of work can happen in research and projects. So I think I'll wrap up now. There's still a lot to show, but just towards the end, I want to just show you another few things about what my company does. Is that we also give robotics and mechatronics solutions. For example, in CET Bhuneshwar, we have given robotic labs like this. So if you want Mitsubishi, KUKA, Fanuc, any of these robots, the entire setup with lab experiments. So you want stacking, you want vision inspection, you want pneumatic chuck wise. We can give these robotic setups. This is Indiasoft installation. So we have a brand name by the name of Expert Labs by Indiasoft. So we have our OEM manufacturers. We give these solutions. So a robotic cell setup will come with a controller like this. So this is a controller, robo controller, and there is a robo programming software. We are also promoting a software by the name of Visual Component. Now, since this is a forum of robotics and automation, there's one particular software of interest which I want to show you, and that is Visual Components. Okay. Now, the reason why we promote Visual Components is a software which has more than 500 types of robots from different manufacturers. So you're not stuck with one particular brand. You could have ABB, Fano, KUKA, Mitsubishi, etc. Not only that, this software also has all the components required to build a robotic cell. Let it be conveyor belt, let it be a AGV machine, let it be a circular overhead conveyor, let it be a pneumatic dispensing machine, sensors, etc. There's a huge list of components which are available. You can see this. So we have automatic storage retrieval systems, ASRS, conveyors, conveyor utilities, robots, machines and lines, CNC machines, etc. And not only that, but the robots which are here, it has got a post processors for a lot of robots. See, in robotics, there are certain things you have to remember. Is that a lot of people say, I want open robo language. People who are trying to do work, I want to connect to MATLAB, I want to connect to Simulink, I want to do this. But you see, that really doesn't achieve anything, because in the industry, what programming language is used for robots? Java, Python, or C#. In the industry, none of them. Sorry. None of them. Actual robots in the industry have their own proprietary programming languages. For KUKA uses KRL, ABB Rapid, Fanuc uses Karel. And if you see the syntax structure, all of them, for the same type of movement, there are different types of the syntax language here. Okay. So Visual Component, the software which I was talking about, has got all these models, and it has got post processors like we have for CNC machines, and you can post process the code for ABB, KUKA, Fanuc, Yaskawa, etc. Okay, and post process for that. It also supports Python if you want to do basic level research work, want to play with the inverse kinematics of the robots, visual components allows you to play around with the inverse kinematics in simulation mode. Yes, it allows you to do that. It supports Python also. And just to give you an idea of visual components, you can see this. It allows you to create entire factory layouts, because what you've seen is basic robotics cell with experiments, interaction of multiple robots, and manufacturing automation where you have loading, unloading of CNC machines, storage retrieval systems, FMS systems, CIM systems. So this software covers the entire length and breadth of this entire topic of manufacturing automation and robotics. So it does the process as well as sim, FMS, and basic robotics also. You can import 3D CAD geometry. You can even build your own customized robots inside the software. Okay, so I think I'll end my session here today. So any questions?
Any questions from participant? Ask one by unmuting itself. Any questions from participant? Ask one by unmuting itself.
See, what I tried to do today was I tried to go by your main title, research opportunities. So otherwise, my college demos are very different. I cover very, syllabus circuits, etc.
uh, I would like to express my heartiest gratitude to our honorable guest, Mr. Pravin Bell, sir, for sparing us time
Thank you, sir.
out of his busy schedule, and to address, guide, and inspire us today. Thank you very much, sir. Uh,
Thank you, sir.
some announcement for participant. Participant feedback form will be shortly displayed on Telegram group, and tomorrow session will start at 10 o'clock. Thank you very much, sir.
Okay, thank you very much.
Thank you, sir. Thank you very much.
Yeah, thank you.